Good morning to everybody. I would like also to welcome you to Athens CMR Level 1 and 2, a 3-day web event organized, as Professor Mavrogenis said, by the Greek College of Clinical Applications of Cardiovascular Magnetic Resonance, as well as by the First Cardiology Clinic. This 3-day web event involves numerous speakers that they will cover. Each speaker is going to cover a specific topic regarding CMRI. I hope that you will enjoy it, and I hope that it's going to be useful to your daily practice. So, the first session is going to cover the physics of cardiac MRI, and our first speaker is Professor Aletras, whose presentation has been pre-recorded. So, please, can we have his presentation?
Hello, everyone. I'm Anthony Aletras, and for the next 40 minutes, we're going to discuss basic cardiac magnetic resonance physics. Hopefully, physics will help you understand why the MR images look the way they do. So let's get started. Here are my disclosures. Our goal is to understand how to generate a magnetic resonance signal, its relaxation properties T1, T2, T2 star, and then how to form an image from this signal. But before we get started, let's make sure that we speak the same language. MRI is all about spinning vectors, so it is important to know about the properties of a spinning vector. In the blue box, you see a vector that has a magnitude of 1. In other words, its length is 1. The vector is spinning at a frequency of 1 Hertz. In other words, it is completing 1 full circle every second. On the right, you see the vector's projection on the x-axis, which is an oscillation, a cosine function. On the y-axis, we would have a sinusoidal function, but it is not shown due to space limitations. In the red box, you see a vector that has a magnitude of 0.5. In other words, its length is half than the blue box one. The vector is spinning at the same frequency as the one in the blue box, a frequency of 1 Hertz. On its right, you see the vector's projection on the x-axis, which is a similar oscillation, but with half the swing because the vector is shorter. In the green box, you see a vector that has a magnitude of 1, same as in the blue box. However, the vector in the green box is spinning at half the frequency as the one in the blue box, a frequency of 0.5 Hertz. Frequency describes the speed of spinning. If we take photos of the spinning vector that is in the green box, then we could capture it when it has completed 80 degrees of the 360-degree cycle. The angle between the vector and the horizontal axis where the spinning started is 80 degrees. We say that the vector has a phase of 80 degrees. At the bottom, you see a photo of the vector when it has completed a full circle of 360 degrees. The vector has a phase of 360 degrees. In the same way that you think of frequency as the speed of spinning, you can think of phase as the position of the vector at any given time when we decide to take a photo. So now, let's talk about spins. The water molecules inside our tissues have 2 hydrogen atoms with a single proton in the nucleus that is positively charged. This proton, this nucleus, spins about its axis. This proton or spin behaves like a small magnet that spins about its axis. The spins inside our tissues are the source of the magnetic resonance signal. If we manage to encode this signal in 3-dimensional space, then we get beautiful images of the heart, such as this one. Let's first describe what happens in a very simple way. All the spins inside the patient's tissues are pointing in random directions, as you see at the top. In the bottom, we have the same picture, but with vectors. Each vector mu represents 1 spin. The patient then goes inside the MRI scanner. You can see here the strong magnetic field of the MRI scanner, the 1.5 Tesla big magnet, the B0. Because of this static magnetic field, you see that the spins, the tissue magnets, align parallel or anti-parallel with this field, pointing up or down. There's about 6 in a million more pointing up than down. Most of the spins cancel out each other. Here you see the resulting picture after canceling out the spins pointing up with those pointing down. The remaining 6 in a million spins are the source of the magnetic resonance signal. These are the ones that will make imaging possible. A more accurate picture of reality is that the spins do not align fully with the magnetic field B0. Instead, they spin about B0 on the surface of 2 cones, one cone pointing up and one cone pointing down. We introduce a Cartesian XYZ system so that we can display on our 2-dimensional slides the 3-dimensional picture. You can see how the X, Y, and Z axis point with respect to the patient's head. The job of the spins is to spin about any magnetic field they experience. They spin faster if the field is stronger. This is given by the Larmor equation. In a 1.5 Tesla magnet, the spinning frequency is approximately 64 megahertz. That is 64 million revolutions per second. As before, more of the spins cancel out, leaving one cone pointing up. In the end, the remaining spins of the patient can be seen as a net magnetization vector pointing along the z-axis parallel to the direction of the magnetic field B0. The net magnetization vector wants to spin about its axis at the Larmor frequency. Why? Because it is made of spins that do this. Now that the patient is in the scanner, we introduce a rotating magnetic field B1, seen here in green. This is done by a radio frequency pulse, the RF pulse. Think of it as a very short version of the radio frequency transmitted to bring music to your radio. This rotating magnetic field is very small compared to the static field of 1.5 Tesla. It's only about 10 millionths of a Tesla. This RF pulse is tuned on purpose to the same frequency that the spins spin. It is applied so that it's on resonance to the Larmor frequency. Remember that the job of every spin is to spin about any magnetic field it experiences. The net magnetization vector M now has to spin about the 1.5 Tesla field and about the RF pulse. Here you see the trajectory of the combined spinning motions. The net magnetization vector is forced to come onto the XY plane. Here inside the parentheses, you see the motion that the net magnetization M does because of the RF pulse alone without the spinning at 64 megahertz. When the RF pulse ends, the net magnetization vector is spinning on the XY plane. As a result of Faraday's law of induction, the spinning magnet generates a small voltage on a coil antenna that we place on the patient. This is the magnetic resonance signal, the free induction decay, the FID, which dies out exponentially with time. This exponential decay is because of spins interacting with one another. Remember, the net magnetization vector is the result of adding all the spins in the tissue. Initially, they all point in one direction, so the signal is at its maximum. As time passes, the spin interactions influence the local magnetic field, and some move faster in red, some slower in blue. They're fanning out, opening out, no longer pointing in the same direction. So the signal is less. In the end, the spins point at every direction, and the signal is zero. The exponential decay depends on the T2 relaxation parameter. This is specific to every tissue and can change with pathology. For normal myocardium, it is about 50 milliseconds. For edematous myocardium, it's about 75 milliseconds. We take advantage of T2 to image intramyocardial edema. If we take into account the magnetic scanner's field inhomogeneity, then the fanning out is faster. T2 star is the relaxation parameter that describes both the tissue and the field inhomogeneity. T2 star is about 20 milliseconds in normal myocardium. The dephasing and loss of magnetization on the transverse XY plane is only the result of an increase in entropy. There is no energy transfer. Right after the RF pulse, the entire net magnetization is on the transverse XY plane. None is left along the Z-axis. As time goes by, the magnetization along Z slowly recovers exponentially. This is done slowly based on the tissue's relaxation parameter T1, and for normal myocardium, it is about 1 second. This type of relaxation along the Z-axis involves energy transfer from the spins to the surroundings. If we inject a gadolinium-based contrast agent, then this energy transfer can be faster, and therefore T1 becomes shorter. We can use this for imaging tissue perfusion and viability. In order to localize the MR signal in space, we use the so-called magnetic field gradients. When we run current through the X gradient coil in the MRI scanner, then the magnetic field inside the scanner changes linearly in the left arm, right arm direction. With the Y gradient, we can change the magnetic field in the nose, back of head direction, and with the Z gradient in the foot head direction. With gradients, we control how fast the patient's spins will spin inside the magnet. We provide three-dimensional space with a unique property useful for creating images. Slice selection allows us to generate signal only from the desired slice to be imaged. We turn on the Z gradient, and spins will spin at different frequencies depending on their Z location. Suppose we want to image the blue slice at Z equals 3 centimeters. We see that the spins there are spinning at 64.000300 Hertz. We transmit the RF pulse at that frequency. Since only the slice at Z equals 3 centimeters is on resonance, only that one will create an FID signal, and the rest of the body's tissues are not contributing to the signal. To localize along the X direction, we turn on the X gradient at the same time that we receive the signal. Here you see the image we want to collect. You see that depending on the position of the spins along the vertical X-axis, they have different frequencies. For example, the black spins in row X equals 3 are spinning slower than the blue spins in row X equals 6. Remember, we don't have this image yet. We're just looking at what happens inside the tissue. Each row transmits a separate signal with a different frequency. Black at 300 Hertz, brown at 400 Hertz, green at 500 Hertz, and so on. Note that the strength of each signal depends on how many spins are at each frequency. 4 for black, 5 for brown, 6 for green, and so on. These signals are received and added together by the scanner's receiver coils, the coils that we have placed on the patient. And we observe this sum, which contains all of these signals. The sum of these signals is fed into a mathematical tool, the Fourier transform, which can untangle the frequencies and show us each frequency's signal strength. so we can tell how strong the signal is at each location along the x-axis. We have a projection of the anatomy seen in the bottom here onto the x-axis. We can get more projections along different directions and reconstruct an image CT style. Or we can use phase encoding instead of more projections. Phase encoding localizes the signal along the y-axis. We already saw that phase is a fancy word for angle. Remember that frequency can be seen as the speed of a car and phase the distance traveled. Think of 6 car drivers next to each other racing. We now care about the distance traveled instead of their speed. We turn on the Y gradient for a short time before we receive the MRI signal. This essentially tells each car driver to push on the gas pedal for a short period of time and then go back to driving as before. We're looking at the columns inside the tissue. Car drivers on the left push less on the gas pedal compared to the drivers on the right, red side. You can see that the clockwise rotation of the spins is higher from left to right, more distance traveled in the right columns. So each column now has its own unique phase. So is the Y direction properly encoded? Unfortunately, when all these vectors are added into our receiver coil, there is no way to untangle them. There are infinite ways how one can go from point A to point B. See, point A to B, the sum and the different ways you can go from A to B. We need to convert phase into frequency, convert location into speed that we know how to handle. Let's see how. First, we ask the drivers to go to the start line and then to increase their speed for a short period of time. Because of the GY gradient, the further away to the right, the faster the driver, that is, the spins, are. From left to right, each column of spins has faster spinning. As a result, when the short period of time of speeding is over, we see increased phase accumulation from left to right with black vectors. At y equals 1, 10 degrees, at y2, 20 degrees, at y equals 3, 30 degrees, and so on. Its vector's length depends on how many spins contribute to that location at that column. But we do not see individual columns. We see the addition of these vectors. This addition, this sum, is useless by itself, as we have already seen. But let's take a photograph of it anyway and remember it. Once that is done, we ask now all drivers to go back to the starting line, and this time to increase their speed for the same short period of time as before, but now double speed compared to before. When the short period of time of double speeding is over, we see increased phase accumulation from left to right with red vectors. At y equals 1, 20 degrees. At y equals 2, 40 degrees. At y equals 3, 60 degrees, and so on. Again, its vector's length depends on how many spins contribute at that location, at that column. Notice that the red phases at each y location are double than the black ones of the previous slide. Again, the red vector sum by itself is useless. However, we take a photograph of it and we store it. When we're done, we ask now all drivers to go back to the starting line and this time to increase their speed for the same short period of time as before, but now triple speed. When the short period of time of triple speeding is over, we see increased phase accumulation from left to right with green vectors. At y equals 1, 30 degrees. At y equals 2, 60 degrees. At y equals 3, 90 degrees, and so on. Notice that the green phases at each y location are 3 times the black ones. Again, the green vector sum by itself is useless. However, again, we take a picture of it and keep it anyway. Last time, I promise. When we're done, we ask now all drivers to go back to the starting line, and this time to increase their speed for the same short period of time as before, but now quadruple speed. When the short period of time of quadruple speeding is over, we see the increased phase accumulation from left to right with blue vectors. At y equals 1, 40 degrees. At y equals 2, 80 degrees. At y equals 3, 120 degrees, and so on. Notice that the blue phases at each y location are 4 times the black ones. Again, the blue vector's sum is useless by itself. However, we decide to take a picture and record this as well. If we now look at all additions together, then we have a new point of view. Each location contributes with a specific rate of change of phase across repetitions. At y equals 1, we get a rate of 10 degrees per repetition. At y equals 2, we get a rate of 20 degrees per repetition. At y equals 3, we get a rate of 30 degrees per repetition, and so on. But look, the rate of change in phase is frequency. It is the same as saying that the rate of change in position of an object is the speed of the object. And the Fourier transform can untangle these frequencies. But this has a cost. These repetitions, black, red, green, blue, take time to do. This makes MRI a relatively slow imaging method. Let's take a look at frequency encoding and phase encoding from the perspective of making a video from photographs taken one after another. If we have 2 cars at the starting line and we use a camera to take pictures at regular time intervals, then these photographs will capture the position of the 2 cars as time passes, right? And if we take these photographs and stitch them together, then we have a video loop and can estimate the car speeds. This is how frequency encoding works in terms of capturing the data we need. Phase encoding works differently. At the top of this slide, we keep the photographs that make up the video so that we can have a reference for comparison. With phase encoding, we ask the drivers to come to the starting line and then tell them to go. We take a single photograph and that is it. We then ask the drivers to go back to the starting line and go with twice the speed. We take again a single photograph at the exact same time as before and end this experiment. We then ask the drivers to go back to the starting line once more and go with 3 times the speed. Again, we take a single photograph at the exact same time as before and end this experiment as well. Once more, we ask the drivers to go back to the starting line and go with 4 times the speed. And again, we take a single photograph at the exact same time as before and end this experiment as well. For the last time, we ask the drivers to go back to the starting line and go with 5 times the speed. And again, we take a single photograph at the exact same time as before and end this experiment as well. If we look carefully, the single photographs that we shot during each experiment contain the same information as the ones that we have for reference at the top above the horizontal line. So we can stitch them together and have a video of the racing cars where we can estimate their speeds. This complicated way to create our video is how phase encoding works in terms of capturing the data we need. If we take all the frequency encoded signals from all the different phase encoding experiments and put them together in a raw data matrix, then we have the so-called K-space. If we do a Fourier transform along both dimensions of K-space, then we get our image. Since this is the dawn of the age of artificial intelligence, instead of the Fourier transform, we can also choose to use the so-called machine learning with a neural network to perform the conversion from K-space to image. This is a paradigm shift because instead of using a mathematical expression, the Fourier transform, we now use a network that resembles in its architecture our brain to perform this task. This genetic network has been trained to perform a specific function, in this case to behave like the Fourier transform. Why should we do this, you might ask? Why should we bother to train a neural network instead of the Fourier transform for this task? To the left you see an image that is reconstructed with the Fourier transform from K-space. In the middle you see how the image would look if the data acquisition was accelerated by a factor of 10 and the Fourier transform performed the reconstruction. Yes, it is 10 times faster, but useless. To the right, you see the same accelerated acquisition, but with a specially trained neural network to do the reconstruction. Amazing how it looks, isn't it? In the future, it will likely become standard practice to use this type of workflow. Acquire K-space data fast, reconstruct an image with artifacts, clean the image, and come up with a diagnosis. Needless to say, each of these steps could be performed by a neural network. Or, much to our discomfort, perhaps a neural network will be able to look at K-space and directly come up with a diagnosis. In conclusion, CMR physics are fun. Understanding the physics means understanding image appearance. There are more complicated physics in MRI than in any other modality, but that makes it more versatile than any other modality. And don't forget, artificial intelligence and neural networks are here to stay. Thank you.
We would also like to thank Professor Aletras for his really very nice and interesting, as always, presentation regarding the basic physics of CMRI. It is important for a cardiologist and for a radiologist who is involved in MRI studies, in cardiac MRI studies, to have to grasp the basic ideas of MRI. So, like this, he's going to be able to distinguish artifacts from an image, to distinguish a good quality of images, less good quality of images, and also to be able to be involved in all this procedure of how to capture MRI images and how to analyze them. So I would like to thank Professor Aletras. As we said earlier on, his presentation was pre-recorded. So now we move to the next, our speaker, who